So welcome to the Circular Industry Talks of the LDE Center for Sustainability. I'm glad to introduce today's presenter, Julieta Bolaños Arriola, researcher at TU Delft in the Industrial Design Engineering faculty. She will talk about safe and sustainable by design circular products, addressing the often underexposed issue of the use of hazardous substances in many products, an issue that will be aggravated in a circular economy where substances might end in products for which they are never intended. Julieta, please go ahead.
Yeah. Hi, everyone. Thanks for joining. Well, like Ruud said, I'm currently doing my PhD at Industrial Design Engineering and Sustainable Design Engineering department. And my overall topic is safety in circular product design. So I not only look at hazardous substances, but I also look at safety considerations for designing for safe repairs for non-professional repairers. So that's the umbrella of my PhD research. I'm in my 4th year, so everything is coming together soon. And but now today we're gonna only talk about some of my findings on the topic of managing hazardous substances or substances of concern. So I want to cover about 5 topics today. It's gonna go quick. I'm not gonna spend a lot of time in each of them, so we have some time to have a little bit of discussion and questions at the end. And we're first gonna try to understand we're going to talk a little bit about how substances of concern are used in products. What are their potential effects throughout the life cycle? Then we're going to talk about current approaches to dealing with those substances of concern and what the limitations are. And then we're going to go on to some of our findings, and we're going to talk about design strategies that we've discovered to deal with substances of concern with products. And then I'm going to show a little bit of the method that we have developed, the Design for Substance Safety method. It's currently still in development, but I can already show a little bit of how it works. And finally, we're just going to discuss a little bit about how we could deal with trade-offs, because it's a recurring topic and a recurring challenge when dealing with substances of concern. So we're going to begin with some horror stories to get you warmed up. So substances of concern are present in everyday products, from clothing to food packaging to baby bottles and all kinds of things, including microplastics. In our research, we have decided to also consider microplastics as a substance of concern. I will explain a little bit more why. But yeah, these substances are everywhere, and they leave traces everywhere they go throughout the life cycle of the product, and they can live in our organisms, and they can also be spread throughout the environment. And some of them have horrible characteristics. So just to give you a couple of examples of what kind of substances we're thinking about. So this is a very common example. So the use of PFAS to give waterproof and stain resistant properties to textiles, which in many cases is needed. So for example, for clothing for professionals such as a firefighter or a nurse or a surgeon, that would make a lot of sense. But in many cases, there is a question of whether we all need PFAS around our rain jacket that we wear on the street. Another example is the emission of microplastics from agricultural mulch films. I don't know if it's clear from the image and if you are all familiar with this, but this is a product that we just put a film of low density polyethylene over our fields, and it improves, it accelerates the production of food and other products, and it creates microclimates and it protects the crops. However, it also breaks into microplastics, which do not degrade or degrade after a really long time, and then they're left there to continue being in our soil. And this kind of practices contribute to the largest emissions of microplastics on land, inland. So it's a different story for water. So for water, that would be, for example, washing machines and the residue from production facilities. But for inland microplastic pollution, it's agricultural mulch films and tires. So this is concerning, no, because this is stuff that we are gonna put in our bodies, and throughout time, the soil quality will also be diminished, and that's gonna bring consequences in our food supply system. Let's go to the next slide. So we have a lot of examples, no? And this is an ongoing discussion, and every day we see more and more headlines of the concerning effects on these substances on our bodies. So it's not a concern that is just out there in the environment. It is very concerning what it does to our environment, for sure, but it's also very concerning what it does to our bodies. So before I jump to that, we hear that these things are carcinogenic, endocrine disruptors. They can present very specific toxic effects in very specific organs. And these effects might not be visible right away, but they can build up over time. And it's very difficult to trace where this cancer that you suddenly have came from, right? So it's difficult to connect and difficult to portray the urgency of how bad these things are, since their effects take so long to get there. And just to talk a little bit about what classifies as a substance of concern, where right now we have systems out there and institutes out there that have classified substance of concern as those that have very specific effects, so hazards. So like I said, carcinogens or mutagens, or they're very persistent and they do not degrade. So those are some examples. But this way of classifying really focuses on on the effect or the potential effect of this substance, but it does not, so it's only based on evidence. So we only classify those substances that we know and we have tested have all of these effects. However, we haven't been able to study all of the chemicals that are out there. And so such a classification narrows it down to substances that we know and do not let us approach substances that we don't know in a precautionary way. So in that sense, and to support designers in considering this in their process, we came up with a different classification. So we classified substances in two ways. One would be those that are intentionally added to the product, either as part of their composition. So for example, the PFAS that go into for example, plasticizers that go into flexible PVC products, or as part of the production that is where the substances are added temporarily, just to give a certain finishing or a temporary function, but it's not supposed to continue to be present in the product later on. And then we have those substances that are unintentionally generated by the product. So those would be microplastics. And microplastics are currently not officially considered substances of concern. However, these microplastics are not just plastic, right? They carry all of the substances and all of the additives that we put in the original product. So if these microplastics are PVC and that PVC was plasticized with a carcinogenic plasticizer, then that's a problem. So we should be considering them as well. So we also see that when we want to move into the circular economy and we want all of these materials, components, products, etc., to recirculate in in these different loops, yeah, we see that substances of concern are really problematic, and they can cause new forms of risks throughout new life cycles of the product. No, so let's say that I want to recycle a cable made of PVC that has been plasticized with a carcinogenic plasticizer, and then I want to recycle that PVC and use it somewhere else. When that means that that we're gonna generate new forms of risk, and then we're gonna generate materials and recycled materials that are also contaminated with the substance. So this is concerning, no, and it puts a lot of barriers in this kind of in this new circular economy that we want to achieve. And so we see here, no, we have all kinds of problems from substance of concern throughout the whole life cycle of a product, no. So during the production of the cable example that I was telling you about, we see that those are emitted, and then that puts at risk the working force, but it also causes emissions to wastewater, for example, or to the air. Then during the use phase, we have a very clear risk example where we have a child who could put the plasticized cable in their mouth. No, we have that once the cable goes into its end of life, we see that if it ends if it ends up in a landfill, then it's gonna emit the substance into the air, or it's gonna go into contaminating the soil or water. But if it's recycled, again, it might end up in the new product. No, so for example, if we say that with the recycled PVC, we made a pot for this plant, then that means that this pot is going to generate new forms of risks throughout its lifetime. And we cannot possibly keep track of all of these problems if we do not design for it not to happen in advance. Now let's talk about the current approach to substances. I quickly wanted to show this. I don't know if you're familiar with this, but this shows how many chemicals are out there in the market, and we have only characterized extensively about 500 chemicals of the 100,000 something chemicals that we have on the market. That's very concerning, because that means that we are only aware that these 500 are risky, and we know their hazards, and we know how they end up in people's bodies and the environment. But for the rest, we count with very, very, very little information. So this is problematic because the industry and research, research in general, we have observed that the focus is on developing non-toxic chemicals or non-toxic materials and alternatives. And having such a focus is concerning, since we may not count with all of the information that we need to classify these new alternatives as safe. So not in not on every case, that is not true for every case, but we do need a lot of information to classify something as safe, and that's not always the case. At the same time, there are very limited guidelines for designers. There's not a lot available for us to approach substances of concern at a different level that isn't the chemical and material level. So if we want to involve designers, then we're gonna need some resources there. So this chemical and material alternative approach has some disadvantages. So, for example, there's not always a substitute. In the case of PFAS, we haven't been able to find a substitute that has the same performance characteristics as the original substance. And in some cases, we just substitute, or companies are forced to substitute certain substances. So, for example, you were using plasticizer A, and now regulation states that plasticizer A is a substance of concern and is carcinogenic and is no longer allowed to be used in products. So then the manufacturer goes, okay, I'm going to use plasticizer B because plasticizer B is not banned, hence it's not risky. And that's a very risky assumption because it's not always true. And in many cases, this substitute have very similar harmful effects, but haven't been banned or haven't been classified as substances of concern, but they are substances of concern. So it's difficult and it's tricky with substitution, and you have to be very well informed that the new substance is indeed safe. So that said, substitution does have a lot of problems. It may be successful in some cases, but we are proposing that there could be a different approach that is a little bit more, preventive, right, rather than reactive. So a good example of this we found is that refrigerants. We used to use refrigerants that were ozone depleting and had a very high global warming potential. And now we have substitute them by non-ozone depleting refrigerants and refrigerants that have a lower global warming potential. However, we didn't stop there. No, these refrigerants are still can still be harmful. So we combined the the substitution strategy with other strategies. So we also made hermetic systems. We also have very clear control manufacturing strategies for refrigerators and other products that use refrigerants. We also have forms of control recovery where we recover this refrigerant and we try to avoid it from escaping into the environment as much as possible. So we think that this is a good example of how we can combine strategies at different levels and approach the substance at different levels. And we think that design could be at the center of that, at making decisions at a product level, at a component level, at a system level, to contribute to trying to mitigate the risks of the substance of concern throughout the entire life cycle. However, today's strategies or design strategies that are available are still recommendations at a material level. So if you look at the eco-design guidelines, you will see that they do touch on the topic of substance of concern, but their recommendation stops at don't use or use healthy materials and don't use toxic materials, and that's it. That's where we stop. So the recommendations aren't at a systems level or have this holistic approach that looks at the entire life cycle, and that's where we want to go. So just to a couple of thoughts of why design is relevant and including designers in dealing with substance of concern is important is because it increases the pool of mitigation strategies. We also might have, designers can have a systemic approach. Designers are trained to look at the product life cycle, but they're also trained to look at functional requirements. They're also trained to look at the context of where this product is going to be used. And they're also trained to observe the relevant stakeholders that are going to be, in touch with this product. And such an approach could minimize, this rebound effect or the trade-offs while maximizing safety. But again, we need guidance, and that's what our research focuses on. We have been working, and I say we because I've been working very close with my supervisors, but there's also another colleague, Maaike Weber, who is working in the exact same topic. So we're working on this together. We have been working in identifying design strategies to deal with substance of concern. We did that by looking into several case studies, several product examples. And we are using our findings, and we're trying to work together with professional designers to develop methods and guidelines for them to be able to deal with substances of concern. So yeah, just to show you quickly some examples of what we found in our studies. We already talked about the cable example, the mulch film example, and the refrigerant example. And we can see that, yeah, we found all kinds of strategies that were employed to control these substances. And we also, well, some of them we didn't find in practice, some of them we only found in theory. So for example, apart from substitution of the mulch film material for example, photodegradable material, we also found other ideas like recovery systems, but also approaches where we reduce the mechanical degradation of the film. I already mentioned the strategies that we found for the refrigerant, but for example, for the cable, we also found strategies that have to do more a little bit with a circular approach of increasing the useful life of a cable, no, and trying not to dispose the cable early. So in that case, that would avoid accumulation in landfills if that's where the cables are ending up. And so we collected all of these insights from all of these cases, and we found that we can summarize the strategies into 3 different groups. So we have the avoid strategies, reduce strategies, and control strategies. And so the avoid would be anything that means that the substance of concern is no longer used in the product. So that would be a hazard approach. So we don't use substances or materials that are hazardous. And the other one, the other level would be reduce and control. And this would be more risk approach. So trying to mitigate the risk of the substance of concern. So that would mean that in reduce and control, we still use a hazardous substance or a substance that we don't know to be safe. But we want to control its potential risks. So that could be by containing it, for example, or by reducing the amount of substance that we put in the product. Yeah, there's different examples here. But the reason they're in a pyramid is because we want to always prioritize avoid strategies over reduce and control. So preferably, we don't use anything that is hazardous. But if we have to use it, and there are cases where you have to continue using the substance, that being for, I don't know, manufacturing cost reasons or performance reasons or etc., then that you still have strategies to mitigate the risks of that substance as much as possible. Okay, so we're reaching, the end. Oh, well, almost the end of the presentation. I'm just gonna show you quickly a little bit of what we've been trying to develop in terms of methods for designers. And with this method, we want to really support designers in mitigating the risks of this substance of concern in the entire life cycle of the product, but also considering subsequent life cycles of the product or the components or the materials that they use. We've made a first version of the method based on theory, but now we went through a second stage where we co-developed the method with design professionals, and that was very insightful. So we want this method to be useful for professional design practice. And I think after this exercise, we gained quite a bit of insight to achieve that. So this method is really design focused. So it's really for product designers and developers. We offer a very clear step approach, but our step approach integrates into current design practice. It has a life cycle circular approach for both analyzing risks and identifying risks, but also for the development of solutions. And we really push to make trade-offs and unintended side effects visible. These are the steps of the method that we developed. And At the back, we see a representation of the design process. It's a very typical representation. It's called the double diamond diagram. And in here, we just put the steps on top of it just to be able to indicate designers where in their development stage they could use each of these steps. We start by identifying the substance of concern if you haven't identified it, understanding it, understanding the risks throughout the life cycle. And at the end of this analysis, we want to be able to have designers understand what the red flags are. So what are the most risky scenarios, and how we can avoid those scenarios. Then we have them, use some of the strategies that I showed you at the top. So avoid, reduce, control. And we propose an iterative process where they have to go through validation steps, where they have to assess their concepts and their new proposals, or their alternative materials or substances. And then we have to see if they pass the test, if they are indeed less risky, or if they have generated new, more concerning trade-offs. So then we have to redo everything all over again until, we have created some form of safe or safer product. So these are just examples of how it would look like. So we offer designers with guidelines to qualitatively assess the risk in each of the stages of the life cycle. We provide them with the strategies that I already showed you. And finally, when they have a new proposal, when they have a new concept or a new material, we force them to reassess whether the risk in the life cycle was reduced, and where in the life cycle we generated new problems. So just to give an example, this is a flooring, a PVC flooring, with a harmful plasticizer that would usually emit the plasticizer into the air during its use phase. However, in this idea, we are covering the layer of PVC with another material, another non-harmful material. So we continue to use the harmful PVC, but we have a new layer. And then that might prevent emissions during the use phase. But that also causes problems at the end of life, because by having this new layer, we make this composite material, which could complicate recycling, for example. So this is the kind of thinking that we want to promote in designers. There are some challenges. There's limited data availability. Designers don't always count with all the data, especially for material compositions and alternatives. So the assessment of these scenarios can be tricky. That means that we cannot do or use accurate assessment methods such as risk assessment and life cycle assessment. And limited data also leads to uncertainty, So at the end of the day, designers have to make decisions with an incomplete picture of what is happening with the substance throughout the life cycle of the product. Other challenges that we have identified is the lack of interest, motivation, or resources. So there's not necessarily interest in design assignments, in design studios from clients to approach substance of concern. So there may not be the priority. And furthermore, the trade-offs may overshadow the mitigation of substance of concern. So let's say that you want to substitute plasticizer A for plasticizer B, but plasticizer B causes your product to triple its manufacturing costs. Then that's going to be an issue. That's going to be a limitation for it to be used and implemented. But we have some ideas on how we can approach all of these challenges. And one is that qualitative forms of guidance for risk identification and the comparison of alternatives could be a good way to start and to get designers started in this process. We also really require improved resources, so improved databases on chemicals or material compositions. We also have found that improving the collaboration with stakeholders throughout the supply chain, could be another source of information. So that could be interesting. However, transparency in those cases can be an issue. So regulation could really support us there. So for example, product passports perhaps in the future could contain all of the information that we require. And furthermore, semi-quantitative assessment methods to accelerate the process of identifying risks and help designers get going. So the task of dealing with substance of concern is not so time-consuming and hence unattractive. And we propose an iterative approach towards uncertainty. Uncertainty is always there, is always going to be there. However, the more we iterate, the more information we're going to acquire. And finally, adopting an incremental approach towards substance of concern could also make it more attractive for companies to implement. This means that instead of having very radical approaches, so for example, instead of a rain jacket with with PFAS, we now use we don't use jackets now, we only use umbrellas. Instead of such an approach, we have an incremental approach on how we can get there slowly. So first by controlling the substance of concern, and then in the future when safer alternatives are available, then we can get completely rid of it. And addressing substance of concern as early as possible in the development process is also relevant, since that's when we can make the most changes. So I think I'm going to leave it at that so we can have a little bit of discussion. And I will share the slides anyway. Oh, and before the discussion, what's cooking? What's next? Currently, Mike and I are working on this semi-quantitative forms of life cycle assessment and risk assessment. So we're trying to simplify these methods just to get designers started. So we're making it really for designers. But that's what we're currently focusing on. And let me know if you have any questions. And I hope this was insightful. And if you give me a second, I will ask if they can be a little bit less loud next door.
Thank you, Julieta. And I have some difficulties with my internet connection, so I sometimes miss some things. But I think it was a very interesting talk on a topic that is really underestimated. Just an initial question on your last slide. You showed some cookware. Any idea what is evaporating from the cookware during cooking?
I don't know. It depends on the material that it's made of. Oh, I cannot go back, apparently. Did I stop sharing? Yeah. Well, there's all kinds of things there, no? It's some form of cooking grade silicon. I don't know what it is. Perhaps some form of aluminium and You know better, I think. You know this case.
Yeah, I think this already shows the complication of the topic and the many things that you might need to take into account, and indeed the difficulties with identifying, but also estimating the magnitude of risks, and leads to quite some questions, I think. But I first would like to give also the audience the opportunity to ask some questions. So who has a question for Julieta?
If I may?
Niraj, yeah, please go ahead.
Yeah, hi, good morning, Julieta. This is Niraj
Hi.
from TNO. I got a question. I'm curious about that iceberg that you showed and said that among thousands of chemicals out there, only 500 have been studied so far and characterized. What I was wondering is about what would be your approach to deal with such a situation? You said that one of the approaches is the better information availability and things like that. But if there is no information regarding such innovative substances, how do you propose to deal with that?
Yeah, thanks for the question. It's a really nice one. Yeah, so what we're proposing is, well, if you are uncertain about the safety of a substance, then that's already yeah, alarming. That should already be a reason for you to take other strategies into account. So if you use a new substance and you're unsure of its safety profile, perhaps you use the control and reduce in combination with the substitution. So let's say that you use a new substance, but you also yeah, try to think, okay, how can I avoid people from being in touch with it? Or if I'm a little bit concerned about its behavior in the environment, then what can I do for this substance to not end up in the environment at the end of life? So that would be, do I recover a certain component? No, maybe the substance is only in a component, in one component of all of the product, or maybe, I don't know, there's some form of yeah, of way that you can encapsulate it, or I don't know. So the idea is to combine those things, and yeah, for the rest, I think as long as you do not assume that because it hasn't been classified as concerning, then it's not concerning, then that's good enough already for you to start reflecting. Does that answer?
Yeah, thank you. Yeah.
Nina, please go ahead.
Yeah, thank you. Thanks, Julieta, for your super interesting presentation. I have a question about the design methods that you showed, that you have co-developed with Maaike. And yeah, the two diamond figure, right? Because I think you really try to aim to also design for subsequent life cycles to really minimize, yeah, the risk of all these substances leaching into subsequent life cycles of any product that has been designed. And how is that yeah, me coming not coming from a design background, how is like this design for circularity, let's say, I think it's also fairly new in industrial design possibly, and like how does like this tradition, maybe more traditional way of thinking, and this also the diamond figure, how does that, yeah, how is your method kind of I don't know, how does it overlap with that new way of
Yeah.
thinking? Because it's already new, and then additionally also the substances, I can imagine it's very complex.
Yeah, I think I understand your question, and I understand the confusion because, well, maybe I'm gonna share my screen again because that would be easier. So if we go back to this one, and so the double diamond at the back is not representing anything else except for the design process. So in the design process, we have sections. For example, we have back here the discovery section. That's where we're doing a lot of analysis, and then the define section goes back to, okay, what are the most important points of those that analysis, and then we go back at developing, where we have ideation phases, and we have a lot of ideas, and then we go and narrow it down back to one idea, and we focus on developing that one. No? So it's the convergence and the divergence of the process itself, and this is only illustrating where in the design process you would take X or Y step. So when is it convenient to understand the substance of concern? When is it convenient to start using the strategies? So that's all this is illustrating. As for the life cycle approach, that's within each of these steps. So for example, when we tell the designer, you have to understand the substance of concern and you have to understand the risks in the life cycle, then we go and provide tools. Like, this is just a very simple example, but we just provide tools for designers to have this life cycle thinking in their process. So when they're thinking about risks, they have to think about risks on each stage of the life cycle, and they have to qualitatively assess each of the stages of the life cycle and decide, okay, actually the use phase is the most concerning one because that's where we have babies biting cables, for example. Yeah, I don't know if this clarifies how about the differentiation between the double diamond and the life cycle approach.
Yeah, no, it does. Thank you.
Anyone has a question?
Jeroen,
I think
you also have a question.
Yeah, I always have questions. Thanks, Julieta. Can you hear me, by the way?
Yeah.
Yeah. I'll not ask anything about LCA.
Good.
Thanks for a really nice presentation, and we love the topic, and we collaborate already. But I was now hearing you about the problems that you have for finding chemical alternatives to substitute, for example. And I was really interested in what ideas you have about that. How can we improve that situation? And then the other thing is, of course, and then you always work with uncertainty. So how do you even manage that in a process where you have so many unknowns and even unknown unknowns?
Yeah. Okay, so the first question was about how to improve information or about information about alternatives, right? Safer alternatives. Well, I really do. Well, talking to designers, yeah, it's difficult to say. I think it's a balance between, yeah, what regulation forces us to share. So there's not a lot of transparency throughout the supply chain in general. And I think some of these databases are either not, yeah, the data on the new chemical or the new alternative is not available, or if it's available, it's very difficult for a designer to understand it. So we would have to start by also trying to understand what kind of information is relevant for designers. So that could also be an interesting approach. Because if you give the designer the chemical structure, they're gonna run away from that. But if you give very clear indicators of why this substance is risky and in which potential scenarios it could be risky, yeah, that could be interesting. Another piece of information that I think is relevant is the release mechanisms of these substances. So how this substance behaves, for example, if it's in a hot environment versus a cold environment. That's useful for the designer because the designer knows where the product is going to live, right? So that kind of information would be useful. So I would make it another research project to think, okay, what exactly does the designer need to know about the substance to be able to do something useful with that information? And furthermore, I would say that, yeah, supporting designers in communicating with their suppliers, and other stakeholders, that would also be interesting. So if the designer doesn't currently know or is not aware of what kind of substances are there, they cannot really ask the right questions or demand information from their supplier. So there also needs to be some form of support there to help them ask the right questions. And then, yeah, if that supplier cannot answer, then you need a new supplier, a better supplier that actually informs you and helps you. And then the second question was uncertainty, right? So I really think that uncertainty is already a part of the design process, regardless of the substance of concern topic. As industrial designers or product designers, really always start from an almost blank page, and they always have to go through a research stage, showed by the little double diamond. And so, yeah, that helps that designers are familiar with uncertainty, with how to deal with this. And a very typical way designers deal with uncertainty is doing a lot of iterations and obtaining more information from their user, if that's where they need information, or from their supplier, or from the recycler, or from the municipality, or from the, they're used to that. So prototyping could be a way of approaching that and obtaining more information. And like I mentioned before in the previous question, another approach is to combine these strategies to not only just leave substitution and trust that this is a safe substance node. It's very often the case that we think a substance is safe or less hazardous, and then 10 years pass and you find out that this was actually a monster, that this was a disgusting thing that you made. So I think designers can plan ahead. So if you don't have all of the information, if you're not sure of the safety profile of the chemical or the material that you're using, then try to think about other mechanisms in which you can, like maybe change your production line if you suddenly discover, that this material isn't suitable. Then maybe you can use maybe you can make it easy to substitute for other materials. Maybe you can, encapsulate it. Maybe you can, I don't know, have a recovery system at the end of life. I don't know. But combining it with other strategies could be a form of prevention of emissions and exposure, I think.
Yeah, thanks a lot. And thanks a lot for sharing your thoughts on this. And I think it's indeed what you also actually indicate is that this is a very interdisciplinary field of work, and looking forward to our joint collaboration there.
Good. Me too.
Any other questions? So one thing that you skipped, Julieta, and that was about trade-offs. You had a slide with challenges, but they all relate quite closely to the method and how to deal with the substances. But in the end, the question is also, why do we use many of these substances? What are the trade-offs behind it? And of course, they are used because they have some function. Sometimes that function is safety, and then I can understand the trade-off, say, with the priority on safety. But in many cases, it's comfort or just cost economics. And how to deal with that type of trade-offs? Would any method that you develop help if we don't have a way to shift priority in those trade-offs?
Yeah, I can also share my screen there. And we go to this. Can you see the presentation? Yeah.
Yep.
Okay, so if we go, sorry. Okay, dealing with trade-offs. So, yeah. So I think, dealing with trade-offs, it depends on the trade-off. So there are different tools and mechanisms in the method that allow you to identify different types of trade-offs. And like you said, the trade-off could be in performance. The trade-off could be in new forms of environmental risk or environmental, of environmental impact, and or new forms of risk. So you either make a change in the product that makes it even more risky to the environment and the health of the people, or you make a change that increases the cost, or in the case of PFAS, you eliminate the PFAS and then suddenly your rain jacket is more of a water coat. So we push designers into identifying those trade-offs, but we have also been thinking about how the combination of strategies could be a potential way of addressing trade-offs. So, for example, and to bring back the example of the refrigerants, there are refrigerants now that are not necessarily harmful for the ozone layer, but yeah, they are highly explosive. So these less harmful refrigerants become explosive. So that's a new form of risk that you generate by substitution. However, yeah, you can design around the substance at a product and a component level to address that new form of risk. So the idea is that we open our head a little bit, and that we approach this combination of strategies. Does that help?
It helps to some extent, but of course, this is a dilemma that doesn't have an immediate answer. So
yeah.
I think I did see an additional question from Nirai.
Yeah, it was more of a remark actually, because I was dwelling on to the point that Julieta made initially about the unavailability of the information and also the containing the risk basically. This is all preventive, and of course, if there is no information available, this would be the best approach. But we can also think about the structures already, about the chemicals that we are using, whether they share some sort of a structural similarity already, and predict based on that how would they behave. Of course, we have certain QSAR models and things like that, and many of them are quite quantitative in their nature, and not that very useful when it comes to the initial stages of your innovation. But still, some sort of a screening type approach for the structural similarity can help us, because there are some out there, and we have been working on them. So that might be really helpful in already telling you what sort of hazard or can you expect if this product is to be used. So that gives a sort of a, like an idea that what the designer is getting into if there is no other information available.
Yeah, definitely. I agree that would be helpful. That resonates with the example of the plasticizers, no? Like any phthalate-based plasticizer is probably going to have a similar behavior. And we have only banned DEHP, and we're considering banning DIMP, but we haven't banned it. So that makes a lot of sense, and that would be a helpful approach for designers. And at some point, we were also thinking about other rules of thumb, no? So if you have, maybe even more simplified, no? So if you have a flexible plastic, if you want to use a flexible plastic, that you already anticipate and think like, okay, but flexible is not an inherent characteristic of the original plastic that I want to use. So I have to add something to make it flexible, right? Or I have to add something to make it waterproof or stain-proof. So by adding stuff, that you also consider, okay, what could be the potential, risks, or what could be the potential hazards of those additives.
Of course. Yeah.
So yeah, indeed helpful. However, in practice, it's very scary to see that companies will, because DEHP and DIMP are so similar, it's very easy, or it's not so costly to substitute one for the other. And one is banned and the other one is not banned. And that's the only thing that companies sometimes think about, right? So I'll keep using phthalate-based plasticizers as long as they let me, So that's concerning when you think about that.
Yeah.
Time, I think, for a last question by Elise.
Yeah, I lowered my hand because I didn't know if we had still have time. But I was wondering because you spoke a lot about microplastics and most of it about additives or chemicals on the plastics themselves. But microplastics, also the physical particle, is harmful to human health. Is it part of the scope of your research, or is it also?
Yes.
And the second question was, because now we are talking from a design perspective, so you look how you have to should design products so that those harmful substances are not transmitted in a circular context, but they can be introduced in the circular process. So while recycling, is it also so people that design those recycled products, do you also work with them to see if during the process, because the design of the original product, they have nothing to do in the design of the recycled product. They don't know what's going to happen afterwards necessarily. And during the process itself, some chemicals can be introduced, or even not chemicals, but if you recycle textile, you can also have a lot, because now we're trying to introduce a lot more recycled fibers in textiles. But we have no idea how they degrade afterwards and generating all those microplastics. And is that also part of the scope? So looking further in the process, not at the start of the product, but in the circular phase.
Yeah, so it is part of the scope, but we treat it as if you are going, we do a scan first, like what kind of materials are you going to use? So we say, okay, are you going to use a recycled material? Where does that come from? Do you have any forms of, information about it? What's the source of this material? Has it been tested, or are you unsure that it's contaminated with other things? So that's already included there in the scan of the product for substance of concern. And for the other question about microplastics, we try to implement it in like having the designer reflect how this substance is emitted throughout the life cycle. No, so and that goes very into detail. No, that you see in which scenarios is this used. No, so for example, in the agricultural films, you want to see, okay, when does this break into microplastics? And
Julieta, I'm going to interrupt you. I am convinced we can talk for quite a while about this topic, and maybe we need another industrial talk about this this specific issue. But we are quite strict in our timekeeping in this meeting because we know that many people have another meeting at 11. So I would like to close this meeting. Thanks you once again for a very interesting talk, and
thank you.
Thank all the others for the participation. And I hope to see you at our next Circular Industrial Talk in 2 weeks with Agata Sarnowska of Collins Aerospace. Thanks, and have a nice